Hello again. Hi. Okay, so last time we went through the introduction of Turing machines and talked about how the object of a Turing machine is not to be a great programming environment. The object of a Turing machine instead is to be so simple that it is extremely easy to analyze it. It's not possible to believe that there are any hidden corners that nobody's ever discovered yet. Well, okay, so we looked at that. That means that learning how to add or learning how to multiply or learning how to exponentiate or learning how to prime factor in Turing machines is going to be very hard indeed, but we get what we want. We get that the device is extremely simple to analyze, and that's what we're going for, so that's what we went for. Okay, we want to maintain, today, we want to maintain that in fact a Turing machine can do anything that any mechanism can do. That contention is called Church's thesis. That's why that's the title of today's discussion, is Church's thesis. The section in the book goes on at greater length. The person should read the section in the book. Once again, the purpose of the slides is only to introduce the material, not to cover it at full depth. But just to introduce it, we're going to talk about it a little bit. Turing wrote his paper that introduced the Turing machine, and on the strength of that, Turing was recommended to become PhD student for Alonzo Church in Princeton at the Institute for Advanced Study, and so that's the connection between the two. That in fact Turing was a PhD student for Church. In any event, so the statement of Church's thesis is that the set of things that can be computed by a discrete and deterministic mechanism is the same as the set of things that can be computed by a Turing machine. The set of things that can be computed by a discrete and deterministic mechanism, like the one you have on your desk, like the one you have in your pocket, like the one that runs your microwave, any of these discrete and deterministic devices. The set of things that can be computed in principle by a discrete and deterministic mechanism is the same as the set of things that can be computed by a Turing machine. Now, some authors, lots of authors, call this the Church-Turing thesis. And in this book, we figure that because Turing has the machine, we can give Church sole possession of the thesis. In fact, the original name is Church's thesis. Collini's original name is Church's thesis. But anyway, you might see it written as the Church-Turing thesis. I want to talk about evidence. So there are 4 points here for the evidence. So I have my little coloring thing, and I'm determined to use it. So 4 points, and I managed to make them all begin with the letter C here. But before I talk about these 4 points, I want to say something about the sort of larger picture. A person who comes to, say, a Turing machine or any of the other equivalent models of computation. A person who comes to those devices and asks something like, well, what can this device do? What can this model of computation do? Finds that a Turing machine or these other models can add, they can multiply, they can exponentiate, they can find the prime factors, they can find greatest common divisors, they can do all the things that you expect that a discrete and deterministic mechanism can do. And at some point, you start saying to yourself, I think maybe this device is as capable as any device can be. So part of what's happening here is experience, but part of it is sort of more in depth than that. So let's talk about the 4 points. Coverage. Everything that people think of as intuitively computable has proven to be computable on a Turing machine. Back in the 30s, when Church had these students who were working on these models of computation, everything they tried to do, these are very clever people, they were able to do. At some point, you start saying to yourself, I think everything that can be done on this device. Now, that's not a totally persuasive argument. It's possible that there's some very clever thing that nobody's noticed yet. Yes, very possible, but nonetheless, it's a pretty convincing idea. In particular, everything you have ever programmed on a computer can be done on a Turing machine because you can write a compiler that translates, for example, C to a Turing machine. So anything that has ever been programmed on any computer in I don't know how long have people been computing since World War II, all of those programs can be run on a Turing machine. I don't know, it's getting more persuasive. Is it possible that all those people overlook some computational possibility? It's possible. I suppose it's possible. But it's starting to look like pretty strong evidence. Convergence. There have been many models of computation proposed by lots of very intelligent people, super smart people, scarily smart people, and they all compute the same set of things. The set of computable functions that we gave in the last video is the same set that is computable by Church's model, so-called lambda calculus, or by Turing's model, or by lots of other models that people have proposed. Random access machines, lots of other models that people have proposed. They all compute the same sets. So once again, you have this building up a pile of evidence. It might not be a knockdown, drag-out argument, but it's starting to be pretty persuasive. Consistency. We got at this a very small amount in the last video. The details of the definition of a Turing machine, the number of tapes or tape heads, the number of symbols, the number of states, all don't change the collection of things that a Turing machine can compute. If, for example, you want that your Turing machine doesn't work with a tape that's infinite, that's unbounded in both directions, but instead you want that your Turing machine works with a tape that's unbounded only one direction. Let me try to write a Turing machine that's unbounded in one direction only. You see why I draw the pictures on the computer instead of drawing them by hand. So you have a tape that's unbounded in one direction only, not the other end. Okay, so there is a location 0 and a location 1 and a location 2. Oh, okay, well that seems like a reasonable model. Okay, well anything that can be computed by the model we studied last time can be computed by this model, and anything that can be computed by this model can be computed by the model that we studied last time. They are equally powerful. Number of tapes. Suppose you have a machine with 2 tapes, 3 tapes, 4 tapes, 5 tapes. Can a 5-tape machine compute more things than a 2-tape machine? No. A 5-tape machine can compute the same set of things as a 2-tape machine. A 1-tape machine can compute the same set of things as a 100-tape machine. Okay? Tape heads. Suppose you have 1 tape with 2 heads on it. Okay, you can compute the same set of things. Number of symbols. Suppose instead of working with blank and 1, suppose you work with blank 1 and 2. Same set of things. Same set of functions. One thing might be easier with done one way than the other way, but you nonetheless can compute the same set of functions. Number of states. Now it's true that a Turing machine with a single state can't compute everything. But once you go to a Turing machine with 2 states, you can compute everything that can be computed by a Turing machine with 200 states. And then lastly, we haven't really talked about determinism very much because you can only talk about so many things at a time. But we'll talk about it at some great length as we move through the course. If you abandon determinism, you can compute the same set of things as you compute if you hold on to determinism. So I'll say that and leave it for a later day. So far that's coverage, convergence, consistency, and then finally clarity. Is that when you read Turing's paper, and I urge you to read Turing's paper, it's a wonderful, wonderful writing. Turing's analysis is persuasive of itself. There's a famous story about Gödel reading Turing's paper in the coffee room at Fine Hall, and he reads the paper, and and when he's done, he throws it down on the desk and he says, "Well, that's it then. The analysis is complete. It's perfectly clear what can be computed and what can't be computed." And Church's thesis is essentially the assertion that it is perfectly clear that what can be mechanically computed, the set of things that can be computed by a discrete and deterministic mechanism, it's the same as the set of things that can be computed by a Turing machine. So if we want to define what can be computed by a Turing machine, we just simply have to think to ourselves, well, what can you do with a discrete and deterministic mechanism? In other words, what can we do with our laptops? Okay. So as yet, there's no persuasive evidence that physically possible systems allow you to compute things that a Turing machine cannot compute. So I mean, here it is, 21st century. We have no persuasive evidence that we can do something that Turing couldn't do in the early 20th century. Sometimes you hear people talk about things involving chucking a computer into a wormhole and it comes out the other side at an earlier time than it went. Okay, we're going to put those to one side as being to my poor mind anyway, not yet persuasive. In particular, note that the set of things you'll no doubt hear on the news about quantum computers, the set of things that are computable by quantum computers is the same as the set of things computable by Turing machines. So we expect that quantum computers will run faster should they be developed, and it sure look like they're being developed, but we expect that they will be no more capable in principle faster, but in principle the same sets of things. So anything that was defined last time to be computable by a Turing machine is also computable by a quantum computer, and more importantly, vice versa. We're going to use Church's thesis in two different ways. So both of them are important to us. The first one is sort of important in a big picture way, and the second one is important in a small picture way, I suppose. So the first point about Church's thesis equates the words computable with computable on a Turing machine. Is that Church's thesis gives our result a philosophical importance. When we produce a result that says no Turing machine can do the following, we are going to contend, because of Church's thesis, that what we are saying is that no one, under any circumstance, can do the following. This cannot be done. Okay, so that's pretty important. Okay. Number two, a sort of smaller picture thing. To prove results about what Turing machines can and can't do, we're often going to argue intuitively. So, for instance, suppose we want to know whether the following function is computable. The input is a number n, and the function returns a 1 if n is prime and returns a 0 otherwise. So what we'll say to ourselves is something like, well, it's obviously computable. I mean, I could write a program to do it. It would only take a couple minutes. You know, even if you wrote it in Java, it would only take a week or two. So that's not bad at all. So to show that function can be computed by a Turing machine, we won't exhibit a Turing machine that does it. Instead, what we'll do is we will exhibit a kind of, usually a sketch, of a regular program that does it. And then we'll say to ourselves, so it is doable on a discrete and deterministic mechanism, and Church's thesis says computable on a discrete and deterministic mechanism is the same as computable on a Turing machine, so it can be done on a Turing machine. And that will get us out of endless hours of trying to do things on Turing machines. Okay? Now that's potentially very dangerous. However, we have so much experience with computation that our intuition about what can be done on an actual device is actually quite good. So for us, the danger is not so much that we will guess something can be done that can't be done. From time to time as we move through the course, we'll say something like, watch out, this does not say X, this says something close to X. But usually the danger is not that we will get wrong what can be computed on a regular everyday computer. Instead, usually the danger is that we will be overwhelmed by detail. If we tried to program Turing machines, we would be overwhelmed by detail very quickly. Okay, so we're going to frequently say this can be done clearly in practice, and so since that means done on a discrete and deterministic mechanism, we're just going to say it can be done on a Turing machine. Okay, so that ends the introduction to Church's thesis. And again, as with all this work, you should be reading this material, should go on to read the material in the book that goes into it at greater depth, and then you should go on to try the problems. Okay, all right, very good. Bye-bye.